In this video, we're going to be working with auxiliary views. First, I'll try to develop the intuition for auxiliary views and then how to incorporate that into your multi-view drawings. There are an infinite number of angles around the object from where it can be observed, and each angle corresponds to a different plane of projection. For example, if we enclose this object inside a dodecahedron, we now have 12 different planes of projection. I'll now pause at random planes of projection and show you the views that we obtain. Look at the views and tell them if that information will be useful to you when that object is depicted as a two-dimensional drawing, compared to what if the object was kept inside a box. And now we are limited to the 6 different views, which can be labeled as top, front, right, bottom, left, back, etc. Look at the views inside the box and how helpful they are in extracting information regarding the object. Will it be easier to convey information regarding the object to a third party using the box's views or the dodecahedron's views? That is not to say that all of the dodecahedron's views are useless. All these other views other than the 6 principal views are commonly referred to as the auxiliary views. We will discuss why they are used further in this lecture. Before moving on into this section, I'd recommend you to recap the box visualization of an object and then the 6 principal views that you can obtain from said box, and then parallel projecting the object onto these views and obtaining the multi-view drawing. These are some concepts that will be referred to in this auxiliary view section time and time. Also remember the 2 axes associated with each plane of projection in the box visualization. An auxiliary view is an orthographic view obtained by projecting onto a plane other than the 6 principal views given to you by the box. You are basically adding a new face to your box and it technically does not remain a box anymore. Now we observe the effect adding an auxiliary view has on our box visualization of the object. Observe the new folding line and the new plane of projection added to our original box. The box with the added auxiliary view is now unfolded. Since the top, auxiliary and right side view are all adjacent to the front view, those 3 are also related views and share a common dimension. Also notice how the whole object is not redrawn in the auxiliary view. This auxiliary view is referred to as a partial auxiliary view, and most of the auxiliary views that you'll come across during your course will be partial auxiliary views. This is because, as you can see in your dodecahedron example, the view obtained in some of the faces of the dodecahedron give a very 3D-esque shape to be represented in 2 dimensions, so it is not very useful to you. Also, now observe the shape of feature ABCD in the 3 top, auxiliary and right side views, and observe the position of the planes of projections relative to that feature in all those 3 views. Can you tell in which view that feature is seen in its true shape or size? It is seen in its true shape or size in the auxiliary view, where the folding line or the plane of projection is parallel to that inclined edge or the inclined face ABCD. Why do we need these auxiliary views? You must have seen in the various drawings that we have drawn in previous lectures. With the parallel projection technique that we employ, the features are either true size or seen as smaller or foreshortened features. A feature is observed in its true size only when the line of sight is perpendicular to the feature or the plane of projection is parallel to the feature/face. So what if you need to obtain the true size of a foreshortened/feature that is observed smaller? We can do that by creating a new view, a new folding line or a new projection plane, which is all the same thing, which is positioned such that it is parallel to the feature we want in true size. We will explore this definition further using the example of a circle observed as an ellipse that we have dealt with in a previous lecture. You should be able to identify that the lines represent the front view of the object and the circle/ellipse represent the right side view of the object. Notice how in the top view the folding line is parallel to the edge of the circle. Hence we get a true shape or size of the face that is represented by that edge, and we see that it is a circle. Now when the same circle is inclined to the folding line, such as in the bottom diagram where it is inclined at an angle of 45 degree, the same circle is now observed as an ellipse in its right side view. So now the question is, what if you were only given the bottom diagram and asked to find the true shape from the edge given in the front view? How would you find out the true shape of the face represented by that edge? To get the true size view of the face represented by the edge in the front view, you'll draw a new folding line that is parallel to that edge or parallel to the face represented by that edge, and then you'll transfer the various distances from the right side view. Remember, you cannot solve this using a miter line because they are not conveniently placed. It's not like the top and the right side view that are conveniently placed at 90 degrees. Instead, you'll have to use the compass/ruler method to transfer the depth distances from your right side view to your primary auxiliary view. Primary auxiliary view and the right side view are two related views sharing the depth dimension. The same colored lines in both the auxiliary view and the right side view depict the depths of the same feature in both the views. This transferring of dimensions between related views is done using rule number 2 or transferring using a compass or a ruler. Your professor might refer to this as going 2 views back to transfer the dimensions. This is because whenever you move 2 views back, you land upon a related view of the auxiliary view. Different types of auxiliary views. It is good to visualize your auxiliary views as new planes of projection being added to your original box depending on which principal view they are drawn adjacent to. First we have the depth auxiliary views. These are drawn adjacent to the front plane of projection. So these auxiliary views are related with respect to the top and right side views. So they share the depth dimension with the top and right side views, which is clearly visible from the folded view of this box with the auxiliary view. We can see that the three related views share the z-axis. The second ones are the height auxiliary views. Here the auxiliary plane of projection is drawn adjacent to the top view. It is related to the front and the right side views. It shares a height dimension with the front and right side views, and when visualized inside our folded box with the auxiliary view, we can see that it shares the y-axis with the front and right side views. Finally, we have the width auxiliary views. Here the auxiliary plane of projection is drawn adjacent to the right side view or the profile view. The auxiliary view is related to the top and front views. It shares the width dimension with the top and front views, and when visualized inside our folded box with the auxiliary view drawn on it, we can see that it shares the x-axis with the front and top views.